Okay, the second speaker is Federico Balducci. Federico graduated in SISSA in 2022 with Antonio Scarlicchio. He then moved to Luxembourg, where he stayed for a year and a half in the group of Campo and Avere. And he's now been for 1 year, more than 1 year in PKS in Dresden, working with Frederick Messner. And he's working on dynamics of many body interacting systems, both classical and quantum control, and also a bit of non-efficient dynamics. And we are very happy to see these black and pink slides that are the colors of Palermo, so please.
Actually, it's blue, but the projector is helping us with that. So, yeah, this is a work that's on the archive that I did with Roderick, who is the director of my division, and Anusha, who is a professor at Boston University, who visited us for a year in her sabbatical. And let me tell you what I'm going to tell you very briefly. I will just motivate that there are some interesting experiments going on with quantum simulators that even if they're not very precise yet, they have a bit of noise and so on, they already are giving us maybe the motivation to look into new phenomena. And one of them is coarsening, that has been so far considered only in the classical case, and in the last year, maybe 2 years, people have started thinking what happens if you add quantum fluctuations on top. Coarsening is basically phase separation, when you see the phase into another and it grows. And so then I will explain you through an effective model what might happen in this experimental setting. We believe that we found an explanation for some features observed in the experiments that puzzle the authors of the works. And then I will show you a bit of numerical results that point in the direction that we propose. So let me start from the motivation. Very broadly, there are now platforms that allow you to simulate the dynamics of quantum systems, be it discrete or real, or continuous. And this has been already motivating a lot the community. For example, in 1D, these 1D systems, like the famous Newton-Cradle experiment, pushed us to rethink about thermalization and integrability. But the kind of questions that you can ask in 1D is kind of narrow. Instead, if you go to higher dimensionality, which is now possible in many different simulators, you can start asking more complicated questions. For example, what happens if you have a model with frustration or glassiness? Or, in particular, what I will do now, what happens when you also have an ordered phase at a finite temperature? Because in 1D, if you go to a finite temperature, usually you lose order. While in 2D, order is stable, and so you can have an interplay of a global order parameter with quantum fluctuations on top. So, this is exactly the question I want to ask. What happens if you have a quantum ordered phase with a definite order parameter and you make it evolve in time with unitary evolution? And so let's go to the simplest model that displays the feature. So you have to think of the two-dimensional transverse field quantum Ising model. Usually this model is taught in 1D where it's integrable. In this case, it's not integrable because it corresponds to the 3D classical Ising model, if you want, for the ground state phase transition universality class. And now the question is, what happens if you want to look at the evolution generated under this Hamiltonian in the quantum ordered phase? Well, strictly speaking, the quantum ordered phase is at 0 temperature, or if you want, I'm using it now energy because I'm thinking my system in the microcanonical ensemble, I don't want it to be coupled to a bath. And since the ground state is an eigenstate, there is no dynamics at all, so very boring. However, there are states which are composed by very big patches of an order, which have a vanishing energy density, because they just pay an energy price along the boundary. And so they are effectively as close as you want to the ground state. So we are very deep in the ferromagnetic phase in this case, but at the same time they're quite non-trivial because they are not easily expressible in the quasi-particles of the ordered case, in which in this case would be magnons. So this kind of physics was probed in a recent experiment that motivated us. So this is the reference. It's a Nature paper, so it must be good. This is the phase diagram of the model. I don't know if you're familiar with the Rydberg Hamiltonian. It's different from the quantum Ising I'm showing you, but the phase transition which it displays is in the same universality class. So we actually use the easing for simplicity. But in this case, what we have to think is that you sit on a certain line in the phase diagram on which there is a transition between a quantum paramagnet and an antiferromagnet. Notice that this plot has been switched, but you have to look at the pink region for the ordered phase. That should help you. And what they did was to study how these patches evolve in time. So they prepare, for example, a square patch or a zigzag. They do many of them. And then they let the system evolve at the different values, at different depth inside the ordered phase. And they see at how these patches become smoother and smoother. So if you want, this corresponds to what happens in classical systems when you quench, I don't know, with a Monte Carlo, your Ising model, and then you see that order grows and it smoothens on larger and larger scales with a certain scaling law. And so they could measure, for example, what is the scaling law in this case. Okay, the system is not too big, but quite convincingly, they showed that the area of the largest domain grows linearly in time, and the area of the second largest domain decreases linearly in time, which points at the fact that the critical exponent of this process is 2. Now, this critical exponent is a dynamical critical exponent. You cannot get it easily with any renormalization group technique. This is an old problem since the 70s. But there are some workarounds if you want. And already in a classical setting, it was known that in 2 dimensions, for using symmetry, this exponent should be 2. It's called model C in the so-called Halperin-Hohenberg classification. And since they found the same behavior in the quantum case, it looks like the quantum effects do not change anything in the picture, because at least at the level of universal scaling of things. If you want, you can think that the size of a domain grows diffusively in time. This is a way of thinking about that. However, they also observed some strange features which were absent in the classical setting. So, for example, if you look at how domain size grows in time, they fit, here not very convincingly, but in other plots more convincingly, oscillations. So it's not only that the domain is growing, but it's also oscillating while growing. And the same frequency of oscillations is also found at the level of the global magnetization. So it means that you have a part of a system which is pointing up, a part is pointing down, and they are sort of oscillating coherently. So in order to understand what happens, they simplified the experiment. So they were starting from a collection of patches, and then they considered what happens in one patch at a time. And they again quenched from the deep ordered phase a bit towards the phase transition. And they observed again the presence of oscillations, and both in the order parameter and in the correlation length. Said differently, they are seeding the coarsening process with a different initial state, and they're seeing what happens, and they were finding oscillations that were so far unreported in any study. So what they did in particular, and this is one of the main claims, they extracted the frequency of these oscillations, so the damping rate and the phase, and they noticed that they are minimal, the frequency is minimal in proximity of the quantum phase transition. So what is their idea? Their idea is maybe it is difficult to probe the quantum phase transition directly, because maybe I don't know exactly where it is in parameter space, but I can just perform quenches, fit my oscillations, and see some property of the underlying quantum phase transition. So this is what they claim. In particular, I want to stress that since the quench goes on both sides of the quantum phase transition, they observe a difference in the frequency of these oscillations, which they cannot explain. I mean, they try to by building a quite artificial explanation. So, I already introduced you what was this experiment. Let me tell you what is an easy way to look at these oscillations, at least in our idea. So, yes.
What does the word coarsening refer to?
The fact that, if you want, you can call it domain growth.
Sorry?
Domain growth. It's just a name. It means that if you want, when you do coarse graining, it means that you're looking at your system at larger and larger scales. Coarsening is when your system is becoming ordered on larger and larger scales. So if you want, you start with a lot of small domains, one points up, one points down, they collide, one wins, and So you create larger and larger patches. That's the technical name for the phase ordering process. So, yes. Can you speak up? It's related, yes, it's related. Actually, I don't have a slide on that, but it's sort of related. There will be a dynamical phase transition. That will be part of the final point. So hopefully, if you follow the next few slides, you will understand everything, and so you will be able to sleep for the rest of the talk. The idea is that you can cook up a model which is much simpler than the full Rydberg Hamiltonian, quantum criticality, and so on. So let's just take a energy conserving model, if you want also unitary, but let's say only energy conserving, and let's look at it from a bit farther away. So we all know that the Ising model is in a way correspondent to the Landau-Ginzburg 5 to the 4th theory. In this case, we have one single real field, so not a Mexican net, just a slice. But you want energy conservation. So you also have to introduce a kinetic term, which is this P, which is the conjugate field with respect to phi. Once you have two conjugate fields, you can do Hamiltonian dynamics for those. And what we did, this was actually done also in many other cases, we started by splitting fluctuations with the global mode. And this is doable exactly because you have a system which has an order. So the magnetization, if you want, is the average on all the system of your Z field. And if you just take the average, you can maybe see what is the dynamics of the average in terms of itself, and then what the fluctuations feed back on it.
So
It's the conjugate momentum to phi. So if you want their Poisson bracket is 1.
I thought that the gradient of phi the square was the equivalent of the kinetic energy. That's why.
If you want, it's the d times square of phi, but that would be the Lagrangian. So you perform this Hamiltonian. Yeah. So let's just look at the zero mode, and let me tell you what happens. So if you have this model, it's one particle in a potential. This is the potential. What you are doing by going from the deep ferromagnet to a less deep ferromagnet, you are just changing the shape of the double well. Okay, maybe it also shifts vertically, but I just put it here for simplicity on the same vertical scale. And if you run the dynamics in this case, so you started from the ground state of the original potential, you change the shape of the potential, you find yourself being not anymore in the ground state. You have gained energy because of the quench injects energy. If you run the dynamics, you will just oscillate in this potential. This is really a particle in a potential 1D. Nothing to see. But this is reflected in terms of the magnetization with oscillations, which will be the ones that actually have been observed in the experiment. And since you have quenched inside the ferromagnetic phase, the oscillations take place only on one side. And so there is, at all times, there is a well-defined magnetization, which is positive. You are quenching from the ferromagnet to the ferromagnet, you see oscillations, but still the magnetization is greater than 0, you are in the ferromagnet, this will be damped eventually, you are happy. If instead you quench too much, you might end up outside of the paramagnet, and you can see it from the fact that you have so much energy that you can reverse the total sign of the magnetization, and so if you don't know, if you average over time, at this point you will have 0 total magnetization, which is reflected by the fact that you are outside of the ferromagnetic phase. And the same happens if you quench maybe a bit less. This is exactly the point that I want to make. If you quench a bit less, just to have enough energy to be above this intermediate wall, if you just look at the dynamics of the order parameter, of course, this will go back and forth. Energy is conserved, and so when you will have 0 kinetic energy, you will get at the same height on the right side. But this is just a simplified model. If you, and this, of course, is the shape of the thing. If you add, again, fluctuations on top, what you are doing is that you are starting from your system, which has the energy all in the 0 mode, and then this 0 mode is coupled with the higher modes, and so after a while, it will have dissipated the energy to higher momentum modes. And so after having crossed maybe once or twice the initial the barrier, you might end up in the second on the other side with not enough energy anymore to go back. And this, if you want, is an entropic effect. In order to flip the magnetization, you have to have that coherently all the spins decide to go up or down. But if you have dissipated the energy in higher momenta, you are not able again to do this. And so what has happened here, you have started from the ferromagnet, you have quenched within the ferromagnet, and you end up with a state which has the magnetization globally pointing in another direction. So this is what we call symmetry rebreaking, and I will elaborate more on this mechanism. If you understand this, well, we can go home pretty soon. So let me show you what happens actually in the Ising model. Let's go back to the more microscopic description. So what you would like to do would be to simulate the spin 1/2 model. You can try with tensor networks. I tried as well. It doesn't go too well because of the growth of entanglement. But so let's, again, keep in mind the idea that we want to look at the system from far away, in a sense. We just want to see what happens to the order parameter. So if you block the spins, you effectively get a dynamics for these larger spins, which, you know, like Susie was doing, it's basically sending the spin representation to a larger number. And there is a sort of controlled way of doing this, rather than in this form here that is suggestive of maybe Wilson's renormalization group, which doesn't work in the dynamical setting. You can just send actually the spin representation of each spin to infinity, and this is a controlled classical limit that you can maybe then also do perturbation theory on top by adding quantum fluctuations perturbatively. Now the interesting bit is that since the model as a Hamiltonian in the quantum case, when you do the classical limit, you also get an Hamiltonian in the classical limit. And so the dynamics that you get in the end is not anymore unitary, but just energy conserving, or if you want, symplectic. And this can be integrated easily numerically, so that's what I did. And this is, again, the same pictures that I showed before for the 5⁴ theory, but in terms of the spins. So I quench from very deep in the ferromagnet to closer and closer to the phase transition. And again, I find the same kind of behavior. So if I quench just a little bit, you get oscillations which stop pretty close to where they started. But if I quench more, but still I remain inside the ordered phase, it might be that these oscillations are 0, and so it means that at late times, you get effectively a reversed sign of the total magnetization, or in some cases, quite puzzlingly, it was quite puzzling that you also maybe getting 0 total magnetization, even if you quenched well within the ordered phase. Of course, in the paramagnet, everybody's happy, oscillations go to 0, and you lose the order altogether. So the idea is again the same. You want to look at the motion of the 0 mode, and to get the 0 mode in this case, you just have to do the same, like basically take each spin equal to the other ones, because you cannot see any difference between any spin. And before we were getting one particle in one dimensional potential, here you get a particle in the sphere because you have a spin. This is the usual Lipkin-Meshkov-Lick model that you might have encountered from the decay model. And again, there is this idea of precessional dynamics that also Susie was presenting. Basically, you put each spin equal to each other, because if you are in the 0 mode, you cannot distinguish any finite distance. So the field that each spin feels, which would come from the nearest neighbors in the many-body case, in this case, it's just the field that the spin generates on itself. So you reduce, it's really the mean field approximation, if you want. So again, yes, but it's painful. Like it's really painful in practice. You can do it. That's why we actually did it for the 5⁴, because it's much shorter and it gives you the same results. Well, if you want to do it for a spin model, which is a bit more representative of the experiment, it's more painful. So yes, if you now plot the evolution of the mean field, so of this Lipkin-Meshkov-Lick model on top of the full 2D dynamics of classical spins, you see that the frequency is well captured by the mean field model, which is telling you in a way that the short-time dynamics is not accessing the physics of the many-body phase transition, because this is captured already at the level of mean field. So there is another type of transition taking place, influencing the dynamics at short times. It's not that you are probing the properties of the full model. And indeed, if you extract the frequency or the damping of these oscillations, you find that the numerics of the two-dimensional model, which are these dots, coincide with the mean field, which is this gray line. And this is quite distinct from the actual phase transition of the model. So in this classical case, we can simulate the system with a much greater accuracy, much greater system size. We can distinguish this happening. These two are numerically close, and in the experiment, they couldn't see the difference. I mean, maybe yes, maybe this point is this is the minimum and is not coinciding with the ground state phase transition. But I mean, it's difficult to really take a conclusion from this. And so yes, the point that I want to stress is that the transition that this drop in frequency that you're seeing from short-time dynamics is not given by the dynamics of the full model, it's just given by the dynamics of the mean field model, which itself has a dynamical phase transition, which, however, has nothing to do with the thermodynamical one. And also, the ratio of frequency of 1 to 2 that you can see on the two sides is well explained in this framework, simply because if you are oscillating only to the positive side of the magnetization, you have to go around a certain distance, and if you oscillate on both sides, you have to go around double the distance. So the factor of 2 is quite immediate. Just a couple of pictures to show you what happens in practice, maybe to corroborate a bit the intuition. So I've showed you that short-time dynamics makes you go with positive and negative magnetization, but of course you are feeding the higher momentum modes. You are pumping energy from the zero momentum to the higher momentum modes, and this will lead you to lose the order at a certain point. If you want, you can also think of this as the system passing close to a very unstable point in phase space. And so after a few oscillations, you will decay. And the point is that you decay on something which is not the long time distribution. You decay on something which is just depending on where you started. If you had a little bit of a fluctuation on one side, you might have decided to point on the plus direction. If you had a fluctuation on the other side, you might point in the down direction. And then when the system finally can talk at all scales, only after that, only after a longer time, you can establish again a full ordered pattern. So, said differently, there is a dynamical phase transition that governs the short dynamics that leads to losing the order that you started with, and then you need a long time, determined by the coarsening process, for re-establishing again the global order in the system. And this depends quite finely on the quench parameter. So you can see that 2.2 and 2.22, you might end up on two different completely final states, a state that points up or a state that points down. And this is reflected, if you want, by the final value of the magnetization plotted as a function of the quench parameters. If you want, the only way of knowing where you will end up, whether you will end up with an up state or a down state, is solving the dynamics of the system itself. It's not easy to predict. And yeah, let me just skip this. So let me conclude. I showed you what happens when you quench a system that also has a global order. This represents a simplification because you have a field which is giving you a lot of information about the system, and it also evolves according to a certain amount of self-consistent dynamics. So you can solve the system exactly, at least for short times before full chaos develops. And we think that this kind of explanation can explain some observations that were made in experiments recently. And also, the interesting thing, at least for us, was that an experiment which had very short simulation times because the atoms were lost and a lot of noise and so on, still managed to stimulate us to find some new phenomenon that takes place also in other contexts. For example, in the classical realm, I showed you only classical simulations. So in a way, it's still pushing the field to ask new questions and more interesting ones. We've done a bit of extensions of of this framework. I've showed you only classical numerics. We are trying to do the actual quantum numerics. We also try to see what happens in more complicated models with a symmetry that is not only Z2. And if you want also a nice take-home message that you have is that you don't have to look for the most complicated explanation in some cases, like they were doing in this paper. They were claiming that the full quantum criticality is at play, showing a strange behavior. You can actually use simple models also in situations that might be complicated at first sight, like a two-dimensional quantum model, which is the farthest away you can think of a mean field explanation. Still, using mean field gives you the first idea of what might be going on. So with this, I would like to thank you.
Have people looked into different dynamics of these sort of questions? So, I mean, so when you watch a transition, you have, at the end, your university, the thermodynamic level, and the mind characteristics. And I was wondering whether people have looked into